Hello everyone, thank you for your time. My name is Stefanus Agus from Singapore Management University. In this occasion, I would like to talk about CocciEvolve, which is a tool to automate the update of deprecated Android API by learning from a single update example. This work is a collaboration between Singapore Management University and the India Institute. First, I would like to talk about our motivation behind creating CocciEvolve. Android API deprecations are widespread and non-trivial and time-consuming to update. Moreover, due to Android fragmentation, we need to preserve backward compatibility when updating Android APIs to make sure that our apps are working with older Android versions. Due to this problem, an automated approach for updating these APIs will be beneficial for developers. Such approach will require an automatic detection and update of deprecated API. So there was a previous work on this topic by Fassini et al. In 2019, in which they proposed a tool named AppEvolve. AppEvolve provides an automatic update by using before and after update example and creating generic patches from these examples. However, a study by Tung et al. In 2020 shows several limitations in AppEvolve. First, AppEvolve requires both before and after update examples, which limits the amount of example usable for the tool. Secondly, AppEvolve requires manual configuration for its update, which is also time-consuming. Lastly, AppEvolve requires its example and its target file to be updated to have a similar syntax or it will fail to produce any update. So, due to these reasons, we decide to create a more robust automated Android API update. So then we create CocciEvolve. CocciEvolve utilizes CocciNel4j and its semantic patch written in SMPL or semantic patch language to provide a readable transformation. CocciNel4j is a recent Java port for CocciNel, a program matching and transformation tool that is used to aid in the evolution of Linux kernel. The semantic patch is written in a similar syntax with diff, so that it can be easily understood by most developers. CocciEvolve has several improvements when compared to AppEvolve. First, CocciEvolve uses code normalization to mitigate syntactic differences between the target code and the example code. And then, CocciEvolve only requires a single after update example, rather than both before and after update example. And third, CocciEvolve provides a readable transformation through SMPL script, which makes the transformation easier to understand. So let's see, first, what is before and after update example, and why CocciEvolve is capable of using only after update example. So in these pictures, the top picture is an example of before update example, while the bottom picture shows an example of after update example. So we can see here that in the after update example, it already contains both the updated API addition and the deprecated API in the form of if statement. The if statement itself contains an Android version check. This kind of statement preserves backward compatibility in Android API usage. So based on this after update example, we determined that by using only the after update example, it is sufficient for CocciEvolve to create a working update because it already contains both the API definition. So next, I would like to show you the general architecture of CocciEvolve. So there are two main pipelines within CocciEvolve. The first one is the top one, the create update patch pipeline. It takes as inputs the after update example file and the API usage change, which match between the deprecated API and the updated API. This pipeline will normalize the example file and extract the updated API block. And then the updated API block is then used to create the update semantic patch. The second pipeline on the bottom pipeline is the apply update patch pipeline. In this pipeline, the target file to be updated also goes through the same normalization process. Then, the update semantic patch is applied to the normalized target file. This will result in the target files being updated. In the next few slides, I will show you the details of each process. Let's first take a look at the code normalization process. Code normalization is needed to mitigate the problem of syntactic differences. Code normalization removes syntactic differences by performing variable extraction. Variable extraction extracts the API arguments into variable assignments. An example of this is given in this image. In this example, the variable time picker is used to invoke the API set hour with the argument last hour plus 1. Using the variable extractor, we extract these variables into the following normalized code. The argument last hour plus 1 is pulled and assigned into the variable parameter variable 0, while the variable time picker is pulled and assigned into the variable class name variable. From this normalized after update example, we can then create the following semantic patch update script. We see here the update script that was created from the example file before. So this semantic patch comprises of two main sections: the meta variable declaration and the change to be made in the source code. The meta variable will automatically match to the actual program elements based on the declared types of the meta variables. The change to be made is written in fragment of Java language, in which the line starting with the plus annotation defines the code that should be added, and the lines without the annotation add context to the semantic patch. Next, I want to show you an example of the transformation process for the target file. So in this image, we can see a block of code containing the usage of Deprecated-API set current hour. First, we normalize this code, resulting in the following code. We can see here in the normalized code that the parameter variable are pulled and put into a variable assignment parameter variable 0 in class name variable. So next, we apply the semantic patch into this normalized code. We can see the match between the meta variables and the actual program elements in the bottom image. For example, the meta variable ident0 is matched with the parameter variable 0, while the meta variable expression 0 is matched with the expression get current hour plus 1 and etc. Then, after we apply this semantic patch into the code, we get the following results. So we can see that the update result contains both the updated API and the deprecated API in the form of if statement, which contains the Android version check. So next, to evaluate CocciEvolve performance, we evaluate and compare the performance of CocciEvolve against AppEvolve on 112 target files from 10 different APIs acquired from GitHub. During this experiment, CocciEvolve managed to create 96 successful updates and only 16 failed updates, while AppEvolve only managed to create 20 successful updates. Next, we would like to discuss the current limitation of CocciEvolve, which makes the failed update. The main limitation of CocciEvolve is its incapability to resolve the values of out-of-method boundary variable. This problem occurs because CocciEvolve only works in a method scope. In this after update example of request audio focus API, we can see in line 10 the updated API. This updated API used the variable request in line 9 as its argument. However, the request variable is created from the getAudioFocusRequest method of the AudioFocusRequestAudio object. This object and its method is located outside of the try-to-get-audio-focus method, which is the method scope CocciEvolve currently working on. When attempting to create an update patch using this example, CocciEvolve will provide an incomplete update patch as follows. In this update patch, we can see that in line 11, the new parameter variable 0 uses the value of request object. However, the request object will not be accessed in the target file, thus resulting in incorrect update. So in conclusion, we emit the tool CocciEvolve, which overcomes the limitations of AppEvolve through the code normalization to mitigate any syntactic differences, only requiring a single after update example, and readable transformation in the form of semantic patch. We have tested CocciEvolve performance on 112 target files and managed to create successful update for 96 files. For future work, we would like to remove the variable assignments being introduced by the normalization process, and we will also plan to handle the problem of out-of-method boundary variables, which limits the example of after-update code that can be used by CocciEvolve. So once again, I want to thank you all for listening to my talk. If you have any comments, question, or suggestion, feel free to contact us in these emails. Thank you.